Okay, so yeah, it's called the sign test. A couple of things you need to know before we start looking at it. First is that it's as I say, it's a mathematical method. And what we are looking for is something called significance. What does significance mean? Importance, yeah, general. The normal understanding of the word significance is something important. The word significance has a special meaning within mathematics, within psychology. And if something is significant, it means it's almost statistically tested and found to be true. I don't like to use the word proven, but it's found to be accurate. And so that's what we're looking at here. We are looking at mathematical significance. So basically, we're looking at results. Okay, so we apply this to psychology. We get our data, and we need to apply tests to that data to tell whether we have a statistically significant result, a mathematically true answer, basically. That's what we're looking for. Next year, you'll look at some more methods. So this is just a bit of an introduction to it, and it's called the sign test. Something that you need to know from the outset is that you need paired data. Write that down, paired data. What that means is that one bit of data needs to have a partner to another. So what design are we going to need in psychology to get paired data? Matched pairs would be one. Another? That's not paired, is it? That's independent. You've got one bit of data and another. Yeah, so it's repeated. So you can only, you might as well write that down as well. You can only do this on matched pairs or repeated. Matched pairs or repeated data. And as I say, what we're looking at is, okay, we look at this data and we need to decide, is there a scientific, a mathematical match? So we're going to go through an example today, and this is one of the first things that you do. You develop a hypothesis. And we've spoken about that anyway. You know that experiments have hypotheses. So the hypothesis we're going to work on today is looking at holidays and looking at whether holidays affect happiness. Okay? So we're going to pretend we've got ratings of some participants, and we've asked them to rate themselves on a scale of 1 to 10. How happy are you? A week before they go on holiday. And then we're going to ask them again when they come back, how happy are you? To see if going on holiday makes you happier. Make sense? Yeah. That's a good point. Surely they would. So that's a common sense answer, isn't it? Well, how's psychology different to common sense? Looks at the brain more. More scientific. So we test it. We don't just say, yeah, that happens. You need to actually test whether that happens. And okay, what we might say then is, okay, we'll test them 2 weeks after they get back from holiday. Do the effects of holiday last? Or it could be that you get back, that first Monday back at work, you're going to be depressed, aren't you? So actually, it might make them worse. So we don't necessarily know. Okay? So yeah, that's a really good point, actually. Why are we doing this? Well, it's not just common sense. We need to actually test it, and we need to see what the results are going to be. So it might be worth writing that down. I'm going to get you to copy this example. So my prediction, I'm going to do a directional hypothesis. We'll go from the common sense. Going on holiday will improve happiness scores. Okay, that's my hypothesis. So I'm going to ask people how happy they are before they go on holiday. 2 weeks after they get back, I'm going to ask them how happy they are again. And here's my data. I've just done that test. Brilliant. Here's my data. So you can write that down. Okay, so I've asked 14 people. These are my participants, P. 1 to 14. They're my participants there. I've got happiness before, so H before. scale of 1 to 10, and I've got happiness after. Yeah, it'd be worth having the example, I think. So you've got participant 1 was 6 out of 10 happy before they went on holiday, and they were 7 out of 10 happy 2 weeks after they got back. Brilliant. Participant 2 was 3 happy before they went, and 4 happy after they got back. And then it goes on. Participant 3, 4, then 6. Participant 4, though, was 8 and then 6, so they were happier before they went on holiday. You've got a couple more like that. Participant 6 was 7 before and 5 when they got back. Participant 11 was 4 when they went on holiday, and they're 4 again. It hasn't had any effect on them. Yeah, potentially. Good, so you're already thinking about evaluating the study, strengths and weaknesses. You're thinking about control of variables and, individual differences. Brilliant, that's fine. But we still need to mathematically test whether there's a difference or not. We can look into the conclusions afterwards. That's your research methods evaluations coming out there, so that's good. Okay, all with me so far. Does it look like there's a difference there? Does going on holiday make you happier? Can we make a conclusion based on that? Yeah, no. That's the problem, isn't it? Some people might think it does, some people might think it doesn't. We're not 100% sure. Some people are happier, some people aren't. So we haven't got an answer. So that's where this comes in. This is why we need a mathematical method. This is why we need significance. And this is why we actually need to test this data. Okay, so that's why you do what we call a sign test. Okay. It's actually really, really straightforward. Okay? It's an introduction to these sorts of tests. As I say, we will do more next year, and they can get a little more complicated, but this one's a nice, easy way in. Basically, all you do, it's called the sign test, because what you do, you look at the sign. Okay? You look at the sign of the difference. And basically, what we're doing is our results afterwards take away our results before. Basically, has there been an improvement? If there has been an improvement, so we're doing our results afterwards, 7, take away 6, you get positive 1. But you get plus 1. This person has gone up in happiness. So all I'm going to do is put the sign of that number. Okay, so it's a positive 1. So that is a positive. That is my sign. The sign for that one is positive. And then you do that for all the participants. So I'm going to go, participant 2 was 4 after, so 4. And then there were 3. So 4 take away 3. Again, that's positive 1, isn't it? They've increased. So I'm going to put that as a positive. Okay, going down again. Participant 3 has also increased. So there, 6 minus 4 is 2, positive 2. So that's fine. Then we get to participant 4. So they are 6 afterwards, and they were 8 before. So you do 6, take away 8. What does that equal? Minus 2. So what am I going to put as my sign? Minus. It's a negative. So it is quite straightforward. That happens again with participant 6 is also a negative. They've gone down. Sorry, I missed participant 5 there. They increased. Participant 7 increased. Participant 8 increased. Participant 9 increased. Participant 10 went down again. Participant 11 stayed the same. That's quite, so we haven't come across that yet. If they stay the same, you just give them a 0. Okay, we're essentially, we'll see this in a minute, we're going to essentially exclude their data because they've got no sign. Okay, they're the same. Participant 12 increased. Participant 13 increased. And participant 14 increased. Okay, and that is pretty much that's what you need to do for the test. That is the sign part of the sign test. Okay? All with me? Straightforward? Great. What you then need to do is count up the number of positives. I can do that down here. Positives. So how many positives are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 positives. Negatives? 3. And then 0 scores? 1. Okay. We essentially, as I say, we're going to exclude the 0 score because we're looking for a change here in holiday, aren't we? And that person hasn't changed. So we essentially, that's no sign. So we get rid of that. So our sign test, what you take is the lower out of the signs, the lower number. Okay, so we might make a note of that, the lower number. Yep.
It says recorded penetration recorded plus for happier before and minus for happier after.
Yeah.
Is that what I was saying?
No, that's what we've done. Yeah, I think that's what we've done. If you look at the signs, we've reached the same signs, haven't we?
It takes me a bit confused. It says recorded plus for happier before.
Yeah, I see that was mine.
A plus for happier before.
It's not minus.
That's not the happy after.
Yeah. No, that's correct. What we've done is correct. Yeah. Okay.
How do you get sin test equals 3?
Okay, because it's the lower number.
Oh, right.
Yeah, so your sign test, the number that we're going to use for our sign test, the number we're going to use for our sign test is 3, because that's the lower number. Okay, what we do is each mathematical equation is given a number, almost an algebra number, and we're doing a sign test, so it's called an S. Okay, so that's just something that you do. So actually, what we report this as, S equals 3. You see where we got to that? It's just called sign test, it's called an S, so our S equals 3. Okay, brilliant. We've got our, what that is called, again, you will need to know this eventually, is our calculated or our observed number. Okay, because that is the number we calculated, that is the number we observed. So mathematically speaking, that is known as our calculated or observed number. Does that make sense? Yeah, quite straightforward. Okay, so we've got our observed number, we've got our calculated number. Good. We now need to say, well, is this significant or not? Is this mathematically, does that actually mean mathematically there is a difference? Now it looks as though there is, doesn't it? Because there are more signs in one group than there are in the other. Brilliant. Okay, so what we need to do this is look at something called a critical value table.
Right, so you just made those values up, plus equals 10, minus equals 3.
No, it's full of plastic.
Yeah.
Okay, we look at something called a critical value table. Again, it sounds like a big confusing term. It's not that confusing. Basically, a critical value table it's a mathematical table that mathematicians, scientists have come up with that determines whether a particular number is mathematically significant or not. And there are loads of them. And again, they look really big, confusing. They look a little bit nonsense. They mean nothing unless you know what you're actually looking at here. Yeah. So we've got all these numbers. Basically, what has happened is a mathematician or a scientist has sat down and said, well, what number do we need for something to be considered mathematically relevant, mathematically significant? And there are lots of different tests of this. So our test that we've looked at is a sign test. So there is one of these tables for a sign test. So if you turn to page 219 in your book, page 219 in the textbook. There is one in the revision guide as well, if that's the only book that you've got with you. I can't remember the page. I think it's 200 maybe in the revision guide. Okay, and it's the blue table. Okay, the blue table there. help finding it in the revision guide.
So the lowest number is S equals.
Yeah, the lower out of the signs. It's that one there. Yeah, that one there. Okay, so that's our critical value table. So to say that, and the critical value table always stays the same. You'll always have the same critical value. If you're doing a sign test, you'll always look at the sign test critical value table. Okay. So what you need to do from that critical value table is find your critical value. And what your critical value is as I say, it's that number that has been worked out to mean that we have significance. Okay? You need a couple of things to be able to find this. And again, write this down. What you need is your n. Okay? And n, again, it sounds weird. It's algebra. I don't know about you. I didn't like algebra when I was doing maths. But it's really straightforward. N just stands for number of participants. And on its own, that would be fine, wouldn't it? No, N, number of participants, number of people in the study, really straightforward. However, there's something you also have to do with that, because in each case, in each test that you do, there's a likelihood that you're going to get a number of participants that have the same number. And we haven't counted that person, have we? We haven't counted his score or her score. So actually you need to get rid of them. So it's the number of participants minus the number of 0 scores. So you could have, we could have had 4 people here that got the same score. So we'd have to do 14 minus 4, the number of people that got the 0 scores. But here, our number of participants is 14, and 1 person got a 0 score. So we're doing 14 minus 1, so it's 13. So our n equals 13. Okay? So just looking at that on your book, n equals 30, you're thinking, what? Where did this come from? N, algebra. But actually, when you look at it, it's really straightforward. Number of participants minus people that got the same score. Easy. Okay, so our n for this one equals 13. Something else you're going to need to know, so n is one of those terms that you need to know, is the level of significance. Okay, so we've said over here that we're testing for a significant difference. Is it mathematically true? Is there a statistical difference in these groups? Okay. Well, we need to say, how certain do we need to be? What are we going to accept as that level? Okay. You need to learn this. The level of significance in psychology is 0.05. Okay, and that will in most cases. That's the standard, okay? You start off doing research and your level of significance is 0.05. For now, all you need to do is learn that, okay? Level of significance in psychology is always 0.05. We will look next year into more detail at that and on why that is. So do you have a question, Liv?
Yeah, if you said n is the significance, then how is it 0.05?
No, sorry, n is the number of participants. This is something separate. So you need to know a critical value. We haven't quite got there yet. To get your critical value, you need to know n, and we found that 13. You also need to know your level of significance. So our level of significance is 0.05. Okay. Basically, I'll tell you what it means. Basically, it means that we are going to have. We're going to go to 90. We want to be 95% sure of our results. Okay. So that 0.05 is in decimal form, 5%. It says that we're going to allow ourselves this 5% error chance. But basically, you flip it around, and what it means is we're 95% sure our results show what we think they do.
This is to show how sure you are.
How significant your results need to be. The standard in psychology is we want to be 95%. That's pretty sure, isn't it? We want to be 95% sure. So you flip that round, and what that means is our level of significance is at the 0.05 level. Okay? We've got all of that, and actually, based on everything we spoke about today, we are now able to figure out our critical value.
What's the 0.01 column for?
That would be if you want to be 99% sure,
Actually,
but we don't need to be that stringent. So that's a tougher test. And there are some cases where in psychology you might look at that.
yeah.
In other sciences, they might look at that.
Will it tell you when to use it?
It will tell you when to use it. You need to know standard 0.05. Unless you're told otherwise, you go 0.05. But it's a good question. So we need to find our critical value. We need to find the number that we're going to look at in this table. And we've now got all the information we need to do that. Okay? So the first column there says n, doesn't it? So what's our n? It's 13. Yeah, n is 13. So you need to scroll down there to 13. We're looking at 13 participants. Okay? The next thing, if you look at the top of the table, there are a couple of sentences. Yeah, Katie's already noticed that, well, you've got columns here for 0.01, 0.02, 0.10, but there's only one for 0.05. So that alone should tell you that you're going to look at the second column. Okay, so you're looking at n, and then in the second column. Okay, but just going back slightly, if you look at the top, it says level of significance for a one-tailed test. Does anyone remember what a one-tailed test is? What type of hypothesis is that? One direction. Yeah, so it's directional. And we've got a directional hypothesis, haven't we? We've stated what we think the results are going to be. So a one-tailed test, the directional hypothesis. So, and that should give you more confidence that you're looking at the right area in the book. So we're looking at level of significance for a one-tailed test. We've got directional hypothesis, and it's the only one there that's 0.05. And I've just told you we need 0.05. So what's our critical value in the table going to be? 3. Good, well done. Our critical value is 3. Okay, because that's what it says in the table. Did you get that? Yeah, our n was 13, our critical value is 3. Brilliant, we've done pretty much everything that we need to now in terms of kind of maths, working things out. The last thing that you need to do, if you read the sentence below the table, that is going to tell us whether our results are significant or not. Okay, and the sentence below the table, again, it sounds confusing when you first read it, but when we start actually interpreting it, it's quite straightforward. So, calculated value of S must be equal to or less than the critical value in this table for significance to be shown. Okay, about half an hour ago, that would have been complete gobbledygook to you, but now you should be able to start piecing those bits together. So, what is our calculated value of S in this study? Is 3, because that's here, isn't it? Calculated value of S is 3. So what it says there, calculated value of S must be equal to, so it must be the same as or below the critical value in the table. So what's our critical value in the table? 3 also. 3 also, because we've just figured that out there. For significance to be shown. So I'll ask you, do we have a significant result? Yes, good, well done. Why? Because 3 is equal to 3. Our calculated value is equal to or less than our critical value. So we have a significant result here. We can significantly say that there is a difference in happiness before and after going on holiday. Okay? So that's all we know at the moment, that there's a significant difference. What you would have to do to make a conclusion is look back at the data and decide what that actually means. So we've just said there's a significant difference. Are they going to be happier before or after going on holiday? How would you tell that? Yeah, you need to look back at your scores, don't you? And we'll say, okay, well actually, we've got a lot more positive scores here, so that's more after than we have before. Okay, so we know it's mathematically significant, and then looking back at the results, we can say that going on holiday makes you significantly happier than you were before you went on holiday. Brilliant. We've done all that, and we've got back to the common sense argument that Kieran made before. But at least now we know. At least now it's scientifically proven. And again, that's the difference. That's the difference between common sense and psychology, isn't it? It's putting the research in there, being mathematically sure. Yeah.
You know when it says the minus, the sign test, and it says equals the low number?
Yeah.
Does that mean that it's always going to be the minus, or does it mean the actual lowest between the positive?
Yeah, lowest between the positive and minus. So actually, it could be the other way around. It could be that there are fewer positive signs. So you would take whatever's lowest out of those two. Yeah.
You know when you find the calculator value, so when it was s equals 3,
Yeah.
is that you should just take in the light? How do you get that again?
Yeah, so that is similar to what Liv just asked there. That is the lower out of the symbols. So if you
Zero doesn't count as a symbol.
zero doesn't count as a symbol, and if you have fewer positives, that is going to be your S, and it's however many positives there are. So say we were to double the number of participants we had here, and the rest of them, the other 14, ended up being negatives, all of them, our lower number would be 10.
Yeah.
Yeah?
Or if you get the same number,
If you get, how do you mean, sorry?
if you've got 22 participants, 11 have positive, 11 negative.
That's a really good question, which off the top of my head, I don't know the answer to. I think yeah, that's correct. That makes sense, doesn't it? It wouldn't matter because it's the same number. So you just take that number, and then again, you apply the same results. Well done. Any questions? No? Good. So as I said, if you just look at the board, it does all look quite complicated. There's lots of new terminology and things on there. But actually, you all pick that up really quickly. It's quite straightforward. And that's why I've recorded the video, because actually it's just knowing the terminology. That's all you need for this, really. Okay?